Arrhythmias are typically treated with either medications or with electroshock therapy. Now, on the medication side of things, there are different types of medications that treat arrhythmias, but before we get into that, let's quickly review the cardiac action potentials. So I'm going to draw them out right here. So we have two different types of action potentials for cardiac cells. We have our nodal action potentials, and that means that they work at the SA and the AV node. And we also have our non-nodal action potentials. These work at the non-nodal cells, meaning your cardiac myocytes. And I'm going to write that down because that's an important concept. So they work on the cardiac myocytes as well as the cells that make up the His-Purkinje system. And cardiac action potentials share similar characteristics as action potentials in other parts of the body. So we have the rapid depolarization phase in both of these. We also have the rapid repolarization phase, and it repolarizes down into baseline. And the change in voltage is due to different ion channels being opened during different phases of the action potentials. So let's talk about the non-nodal action potential first. What's going on here? Well, we have phase 0. And phase 0 is this rapid depolarization. And this is because we have an opening of sodium channels. So sodium channels open, sodium pours into the cell, and you get this rapid spike in voltage. At some point, these sodium channels close, potassium channels open. So as sodium no longer goes into the cell, and as potassium now leaves the cell, we're going to enter something called phase 1, which again is mediated by potassium channels. And we're going to get this slight dip in voltage, which brings us into phase 2. And in phase 2, we have calcium channels that open, while the potassium channels are still open. So what's going on here? Calcium is entering the cell as potassium leaves the cell, and the charges sort of balance each other out. So therefore you get this plateau period where there's no change in voltage. Eventually, these calcium channels start closing, and you have a lot of open potassium channels, and this brings you to phase 3, which is your repolarization phase. So phase 3 is this decline in voltage, and it's a repolarization phase caused by a lot of potassium channels being opened, which brings us down to baseline, and that's phase 4. And this is your resting membrane potential, and this is mediated by the cell being freely permeable or open to potassium. So that's the action potential for a non-nodal cell. And again, this is the action potential for a cardiac myocyte or a cardiac muscle cell. What about the nodal cells? Well, at first glance, you'll notice that the action potential for the nodal cell looks a lot different than the non-nodal cell action potential. For one thing, you don't have phase 1 or phase 2. All you have is phase 0, phase 3, which is again your repolarization phase, and phase 4. Now let's talk about what's going on in this action potential. So in phase 4, we have this slow rise in voltage because of open sodium channels. And at the tail end of the phase 4 period, calcium channels start opening. We hit threshold and a bunch of calcium channels open, and we get this large spike in voltage. This is phase 0, and again, this is because calcium channels are opening. There's no phase 1 and phase 2, so we go automatically into phase 3, which is this repolarization phase. And this is mediated by a bunch of opening potassium channels. And eventually we're back down to phase 4, where we have the sodium channels again opening slowly. So again, these two action potentials not only look different because there's no phase 1 and phase 2 in the nodal action potential, different ion channels are open during different phases. Another important piece to point out is that your area between phase 0 and phase 3, this is known as your effective refractory period. It's a window of time when you can't trigger another phase 0 action potential. And I'm going to call it ERP for short. Again, during your ERP, you can't trigger another phase 0 action potential. So basically, it's like a built-in mechanism to prevent the cell from overfiring. And it's kind of like the cell's recovery period. So what would happen if we increased our ERP? Well, you would increase the amount of time between depolarizations. Therefore, you'd increase the amount of time between heartbeats, or when this myocyte can contract. And if you're increasing the amount of time between heartbeats, you're decreasing the heart rate. And I just wanted to point that out because that's how some antiarrhythmics work. And we'll revisit this in a couple seconds. So we're going to talk about 4 different types of antiarrhythmics, starting with class 1. And these are our sodium channel blockers. So remember, in the non-nodal action potential, sodium channels are really important for phase 0. So if you block sodium channels, it takes you a longer time to get through phase 0. So what's happened? Well, before when we had an ERP this long, our ERP is now this long. We've extended the effective refractory period. And like we said before, when you extend the effective refractory period, you're going to have a longer time between depolarizations, meaning you have a longer time between heartbeats, meaning that you're slowing down the heart rate. And that's why sodium channel blockers are great for treating supraventricular tachycardias, which we sometimes call SVTs for short. Examples of SVTs are atrial fibrillation, also known as AFib, and this is a condition where the top chambers of the heart are spasming. You can also use a sodium channel blocker to treat an SVT caused by Wolff-Parkinson-White syndrome, which causes a certain type of reentrant tachycardia. And again, these are just a couple of examples of SVTs that are treated by sodium channel blockers. So the next class we're going to talk about are our class 2 antiarrhythmics. And these are our beta blockers. Beta blockers work because they decrease sympathetic stimulation. They block the beta 1 receptors at the SA and the AV node. So I'm going to draw out a couple nodal action potentials. Now, how does sympathetics work to increase heart rate? Well, sympathetics work by increasing the slope of phase 4. So basically, you're hitting thresholds sooner. And if you hit thresholds sooner, you're going to have more frequent depolarizations. Okay, so I'm going to erase this so we can see how beta blockers work. Beta blockers work by blocking sympathetics. And if sympathetics increase your phase 4 slope, beta blockers are going to work by decreasing your phase 4 slope. So actually, it's going to take you longer to hit threshold. Once you hit threshold, the action potential will be the same, but it takes you longer to hit that threshold. So again, by decreasing the rise of phase 4, you're going to decrease the frequency of SA node firing. And since beta blockers work at the AV node as well, you're going to slow conduction through the AV node. So both of these things are going to work to decrease heart rate. And that's why beta blockers are great at treating SVTs. Again, like AFib and even atrial flutter. Beta blockers can also be used for ventricular tachycardias, also known as VTAC. So someone with a history of an SVT or VTAC might be put on a beta blocker to help control their heart rate. Okay, so the next class we're going to talk about are class 3 antiarrhythmics. And these are your potassium channel blockers. These work primarily at non-nodal cells. And where in the non-nodal action potential is potassium important? It's important here at phase 3. So when potassium channel blockers are on board, we're going to get an elongated phase 3 period because we're blocking potassium channels. Now, what does that do? Well, where we once had an ERP this long, our effective refractory period is now this long. Just like with the class 1 drugs, when we increase our effective refractory period, there's more time between depolarizations, meaning there's more time between heartbeats, meaning you are slowing down the heart rate. And potassium channel blockers are great for treating SVTs and VTAC. But something important to note is that your phase 3 of the action potential corresponds to your QT interval on EKG. Since potassium channel blockers elongate your phase 3, you're going to be elongating your QT interval. And elongating your QT interval is dangerous because it can lead to a dangerous rhythm called torsades. And this is a type of VTAC. Torsades is also dangerous because it can disintegrate into something called ventricular fibrillation, also called VFib. In VFib, the bottom chambers of the heart are spasming and nothing's contracting, so you're not pumping blood to the rest of the body. That's why VFib is deadly if it's not treated immediately. So anyone that has a long QT, whether it be from medications they're taking or from a genetic mutation that they're born with, anyone who has a long QT, they stay away from potassium channel blockers because we don't want to throw them into VFib. Okay, so let's talk about class 4 antiarrhythmics. And these are your calcium channel blockers. Calcium channel blockers come in 2 types. You have your dihydropyridine, which is abbreviated DHP for short. And you have your non-dihydropyridine calcium channel blockers. Your non-dihydropyridine calcium channel blockers work at your SA and your AV nodes. So they work at the heart. Where your dihydropyridine calcium channel blockers, these work at blood vessels. Sometimes to remember this, I will erase this O and I'll draw in a heart in place of the O so that I remember that the non-dihydropyridine calcium channel blockers work at the heart. And again, the dihydropyridine calcium channel blockers, these work at blood vessels. They have little to no effect at the SA and AB node. So where in the nodal action potential are calcium channels important? Well, they're important at phase 0. So when you have a calcium channel on board, you're going to hit threshold just as fast, but it's going to take you longer to go through your phase 0. Therefore, you're going to decrease firing at the SA node because it's taking you longer to get through phase 0. So again, because we're decreasing or delaying the slope of the phase 0 period at the SA node, we're going to decrease firing at the SA node. Since they also work at the AV node, we're going to slow down conduction through the AV node. And again, both of these will lead to a slower heart rate. And since we're slowing heart rate, calcium channel blockers work great for SVTs. Now you might be wondering, why don't they work for tachycardias like VTach? Well, that's because in studies they found that potassium channel blockers do a better job at treating VTach than calcium channel blockers. So that's why if somebody has VTach, they're not going to reach for a calcium channel blocker first.